Everybody, welcome to this course on automata, grammars, and computability. So this is the very first video in this sequence. So let me start with telling you what this course is about. So in general, we're going to answer questions like, what is computing? What things are computable? And what even does it mean to be computable? And are there limits to what is computable and what does that mean? So that covers kind of the computability aspect of the course. Other questions include, how do we model a computer and why are models helpful? And are some problems in computing harder than others? And that covers more of like the automata and grammars portion of this class. So I kind of went backwards through here. But all of these ideas are related to one another. So I'll do my best to try to keep things in a logical order with sometimes some forward-looking pieces of information. In a little bit more detail, regarding the automata and grammars, those are ways to create models of computing. So we're going to create models of computing. We're going to start with finite state machines, which can be related to automata, and we're going to see other kinds of machines. And we're going to end up drawing pictures with lots of circles and arrows. Another nice thing that this course has is the connection between computing and math. So we'll talk about things like sets, sequences, logic, and functions, and we're going to use these mathematical definitions to define these very specific, quote-unquote, mechanical models of computing. So we'll take some forays into talking about really math-specific looking things, but those will all be used as tools to understand models of computing. And I do want to point out that the theory of computability influences and guides what we do every day. This is maybe a little bit shocking in this world where I'm literally using my computer to record this video. I have computing peripherals like a mouse and a keyboard, and it's kind of weird to think that there's an actual deep theory that goes into making that. So, you might be wondering, like, why bother with theory? If you do want to be a computer scientist, it's nice to know foundations. It's kind of like how physics relates to mechanical engineering or how music theory relates to performing music. The interesting thing here is that even though physics is hundreds of years old and music theory is hundreds of years old, computability theory is super, super young. We had a lot of milestones in the 1930s, 50s, and 60s. And I have here this image of Alan Turing on the 50-pound note. So he is one of the big names in computability theory and kind of where a lot of what we're doing in computation exists nowadays. And he was alive during the 1930s and 40s. Now, another useful reason to learn theory is just to get a good workout with your mind. Working with logic and problem solving and understanding the big picture, those are useful in just becoming more clever over time and also understanding what you're doing. Even if you're just writing a program, it's useful to know some theory as to why your program may or may not work. And if that's still not super clear to you, if you want to be a computer scientist, there's going to be some area that you get into. So maybe you really get into doing text search and text processing, large language models. And so, if you are interested in that sort of thing or compilers, then That's an application of computer science theory. You might be interested in antivirus, intrusion detection, input validation, things like that. That is security. And cybersecurity is big right now. In general, just if you're into programming and you want to find bugs, you want to know things like, can I find all the bugs? Do I have to run my program to be sure what it will do? How do I ensure my program is correct? How do I know how complex some algorithm is? And then another thing that's useful is modeling. So you might want to model an entire system and prove things about it. This is what the entire internet is built off of, protocols which have formal models and specifications. So these are just some examples, but these are different ways to apply the theory that we will learn. And that really gives you, I'll use the word again, the foundation. So now let's go into the actual class contents for automata, grammars, and computability. I've kind of talked about the big picture, so now let's look at all of the little topics that are going to help us build up these mental models and get real strong in these foundations. Today, since this happens to be the first video, we're going to start with just proofs, computability, and languages, some of which I am expecting is review. If you're not so familiar with it, it's okay. There is time to, pause and look that stuff up and get some practice with it. And then beyond that, we're going to talk about things like automata of various types, regular expressions, non-regular languages, context-free grammars, Backus-Naur form, push-down automata, and Turing machines decidability, P and NP. And I kind of went over that kind of quickly because, and it's grayed out, because of course that's not what this video is going to be about, but that gives you a sense of all these little topics that are going to go into understanding automata, grammars, and computability in the end. So let's go ahead and look into specifically today's work, which is proofs, computability, and languages. And I recommend that you read Michael Sipser's Introduction to the Theory of Computation, chapter 0 and 1.1. So let's talk proofs. To be able to talk about computability and automata, we're going to need some basics from set theory, logics, and some particular proof techniques. The ones we'll use the most are going to be contradiction and construction. So here I'm going to do some review of some vocabulary, which is also in chapter 0 of Sipser. And we're going to see something as well on this slide for the first time, which is going to be some underlined words so that you can actually fill this in using a guided notes handout. So let's take a look. A set is a group of unique and unordered elements. We say A is a subset of B if A is contained in B. So here we have the symbol, which is contained in, which means all of the elements of A are also elements of B. We write the elements of sets in braces. So here, for example, curly brace A, comma B, comma C, close curly brace. And finally, if we want to say X is an element of A, we write X in A. So X and then this sort of in symbol, which kind of looks like the letter epsilon, in A. So here you can take a moment to write down these words if you are following along on the guided notes. And lastly, a set with no elements is called the empty set, and it is written as this sort of circle with the slash through it. a little bit more with set notation. So for some given set y and a predicate p, we can write q is equal to x, and then this line such that, the line's called, I read it as such that p of x, which you would read as q is the set of all x for which p of x holds. So a predicate is something that ends up being either true or false about x. For example, emails is the set of x such that x is a valid email address. The set t's is a word such that word is an English word starting with the letter T. And z's is word such that word is an English word ending with the letter Z. So here I actually wrote everything out in English description, but a lot of times we have mathematical predicates, and you can actually write it as just p of x, as we see in the notation here. So it just depends on what that particular problem is. So next, let's look at what it means to be the complement of a set. It's basically just all the elements that are not in a set. And it's written like this. So you'll see here the set is y, and I have a little bar over it, so not y, and that's equal to the set x such that not x is in y. Okay. So now we're going to look at the notation for certain set operations. The first one is going to be called union. The second one is called intersection. And the third one is called difference. So the first one, union, the notation looks like this. Y union z is equal to x such that x in y or x in z. So y, and then the union symbol kind of looks like the set cup thing. Z is equal to x is in y, we've seen in before, and then the symbol or x in z, which means either the element x was in y, or it was in z, or it was in both sets, y and z. The next one is intersection, which looks like this. So a couple of symbols off. Now I have y intersection z, which is this cap looking symbol, set cap. And I have y set cap z is equal to x such that x in y and x is in z. So here, notice that the symbols changed. I have cap and then I have and here. The final operation I have on the slide is called difference, which can be written as y minus z, or y set minus z, which is a backward slash, is equal to x such that x is in y and not x is in z. So let's just look at an example to clarify what these set operations mean. Let's say that the set y is going to be the set of words that start with the letter T. So something like toy, took, tremble. These are words that start with the letter T. And let's say that the set Z is the set of English words that end with the letter Z. So maybe something like jazz, quartz, things like that. So what you'll notice here is that if you take the intersection, which is the part that kind of overlaps between the two of them, you can have the word topaz. Right? So that's a word that starts with T and ends with Z. Another thing you'll notice, though, is that the other examples I have So like tremble, that's a word that is in y set minus z, right? Because tremble does not end with a z. And similarly, words like quartz, right, that's in z set minus y because it ends with a z, but it does not start with a t. So here, basically the part that's in the center that covers both of them, that is what's called the intersection. So, and we write that as y intersect z. The part that's without, right, is going to be set minus. And then you can have words that are in either of the two. So all of these words that I've written, actually toy, took, tremble, jazz, quartz, and topaz, those are in Y union Z. So moving on, let's talk about the definition of the word power set. Given a set A, we call the set of all subsets of A the power set of A, which you can write it as 2 to the A. And another way to write it is P of A. So here I have P of A is equal to 2 to the A, which is the set of X such that X is a subset of A. So something that's new here is now the elements are now also themselves sets. Let's look at an example. P of 1 and 2 includes the empty set, which is a subset of all sets, just 1, just 2, and 1 and 2. And you'll notice here that if you have a set that has n elements in it, the power set will have 2 to the n elements. Good. So moving on from sets, let's move on to talk about logic. So logic, for us, we're going to be thinking about Boolean logic. So Boolean logic is a mathematical system which is built around values true and false, which you've likely seen in previous computer science classes or math classes. Now, there are some symbols associated to that kind of logic. So there's the first symbol, which is a not, and it's the negation. We saw that earlier when we saw the set complement. There's and, which means both things have to be true, or, which means one or the other or both are true. And then we have this thing called implies, which we're going to use when we're doing proofs, and it's going to say if something is true, then another thing is going to be true. And you can also have a double-headed arrow, which you often write as if with 2 F's, which means if and only if, which means like if you write P if and only if Q, then that means P is true exactly when Q is true. And you'll kind of notice that this looks a lot like set notation because the and looks like that set cap and the or looks like the set cup. So this is going to be very useful to you to basically be able to think about the analogy between sets and logic here. Besides the basic symbols that we saw on the previous page, there's also these logical quantifiers. So these symbols, we only have 2 of them. There's for all, and there exists. So this is pretty easy to remember if you have the mnemonic, which is that all looks like an upside down A and exist looks like a backwards E. Now, this is just here for completeness. Most of the time, when we're going to write proofs in this class, we'll likely just end up using English text for all or there exists, or some other English equivalent rather than using the symbol. but if you like to be terse, these are totally fine to use. And so now with all these like notations and symbols in place, we can start talking about proofs. For this course, it's mainly going to be by contradiction and by construction. So a proof by construction has it so that theorems are going to state that a particular type of object exists, and you can prove this theorem by constructing the object itself. And you'll notice here I'm using the word exists rather than the symbol exists. So let's look at an example of a proof by construction. And I'm just going to use some particular ones that we're going to see later in this class. This is why it's a forward-looking example, which means it may not make total sense what any of the things in it mean quite yet, but that's okay. The theorem is going to be there exists a DFA that recognizes the language B word such that word has an even number of ones. So I know we haven't gone through all of this, but we're basically saying that there exists something called a DFA that recognizes this. And the proof is just going to be draw the DFA. So I'll just have you draw this in. This is going to be the DFA for this particular language. So let's take a look just at the parts of it. I have here this arrow that comes in, and then these circles. This circle has two parts, like a circle outside of another circle. It's got an arrow pointing in, which says 0, an arrow going out, which says 1 to some other state called Q1, and Q1 points back to Q0, and Q1 has to itself an arrow that says 0. All right, so this whole thing, this is what's called a DFA, or discrete finite automata. And it does, I promise you, recognize this particular language. So all I've done is construct the exact DFA that does the thing that I wanted it to do. The other kind of proof that we're going to see most frequently in this class is proofs by contradiction, which basically means that we're going to assume that a theorem is false, and then we're going to show that this assumption leads to some sort of false consequence. So let's do another forward-looking example. And again, I know we don't know what these particular things mean, but we're going to say, let's prove that this particular language, AI, BI, for I greater than or equal to 0 is not regular. And we're going to prove it by contradiction using something called the pumping lemma, which we'll see later on. And since we don't know what the pumping lemma is, let me just show you the structure of these proofs. So we'll write the theorem, and then we'll have a proof, and we're going to say, assume for the sake of contradiction that this particular language is regular. You're going to do a bunch of logic. And then it turns out that all that logic is going to lead to the conclusion that the pumping lemma doesn't hold. Therefore, the language is not regular. But we do think the pumping lemma is true, so it turns out that this is a contradiction. A couple of things to point out here. So I said that we're going to say that the language is not regular, and we're going to assume, for the sake of contradiction, that it is regular. I always start out with proof. When I do proof by contradiction, I always write assume for the sake of contradiction. And sometimes I will do shorthand and say AFSOC. And actually, to be more thorough here, you should also say something like, and the pumping lemma holds. Okay, so hopefully this points out the parts that we care about for that proof by contradiction and gives you a skeleton structure for what we're going to see later. Okay, so now let's go ahead and move on to talking about computability just a little bit. So with computability, we're going to answer questions like, what are the fundamental capabilities and limitations of computers? Another important question is there a problem that no computer can ever solve? So with computability, it turns out, by the way, most problems are unsolvable. The prototype of unsolvable problems is something called the halting problem, which we'll see later in this course. Now, to be able to prove that there are unsolvable problems, we'll need a way to describe programs and algorithms. And that's why we need models and languages. Great. To have a language, we're going to need alphabets and we're going to need strings. An alphabet is defined to be any non-empty finite set. The members of the alphabet are known as symbols of the alphabet. A string over an alphabet is a finite sequence of symbols from that alphabet. Right? So basically, we've seen things like this before. You might say that your alphabet is literally, I'll use capital sigma, and I'm just going to have A, B, C, D, all the way up to Z. So the letters of the English alphabet. And then you can write a string like cat, dog, topaz. So these are all words that are strings over the alphabet of letters of the English language. Great. So now that we have an alphabet and we have kind of this way to form strings from it, we can talk about languages. A language is just a set of strings. A language is known as prefix-free if no member is a proper prefix of another. So by the way, a string is a proper prefix of another if it is a prefix but not equal to the other. So let's continue the English language example. Let's say, you can say that the word dog is in a particular language, the English language, but if just because I come up with some letters, it doesn't mean that it's going to be an English word. So I could say T, X, Y, M. That's a valid string using the alphabet, but it is not an English word. English is not prefix free. You'll notice things like cat is an English word, and so is catamaran. And since those are both English words, it means that English is not prefix free. Good. So let's talk about recognizing a language. We'll talk about what this means in more depth later. For now, I'm just going over the vocabulary. A finite machine M is going to recognize the language A if A is the set W such that M accepts W. An equivalent way to write this is A is equal to L of M. And then final vocabulary for today is a language is what's known as a regular language if some finite automaton recognizes it. So that's all we have for right now. Thank you for watching.